So perhaps one of the most important functions in this class, and probably most of your undergraduate experience, is the exponential function. So just a quick reminder, if we choose to write z as x plus iy, then we'll take as our definition right now, we'll have a different definition later, but right now, we'll take as our definition of complex exponential. So what does it mean to raise e to this power? Well, we're going to raise e to the x, and then we multiply it with cosine y plus I sine y. So this is our complex exponential. Let's see, what's a good color for this? I don't know. Let's do this. And it's a very, very, very important function. So in example 3, we're just going to compute some values. All right, so for a, we're going to compute e to the 0. E to the 0 is e to the 0 plus I times 0, just to be clear. And so with our formula here, it's e to the 0 cosine 0 plus I sine 0. All right, let's fill in some things here. E to the 0 is a 1. Cosine of 0 is a 1. Sine of 0 is a 0. So we get 1 times 1 plus 0. So we get 1. Great. E to the 0 is still 1. And in fact, more is true. Whenever you're plugging in a purely real number, so let's call this like a wiggle or something, if your number is purely real, then it would be bad if this somehow differed from the usual definition of the complex exponential. So let's just check what happens on purely real expressions real quick. So that's going to be e to the x cosine 0 plus I sine 0 if we just use the formula where the real part is x and the imaginary part is 0. That's a 1. The 0 gets rid of the imaginary part, and we recover e to the x. So it agrees with the regular e to the x, or the regular exponential, when you're plugging in purely real numbers. All right, great. Let's try another example. We're going to compute e to the I. And e to the I is, just to be clear about real and imaginary parts, it's e to the 0 plus 1i. So that's going to be e to the 0 cosine of 1 plus I times sine of 1. Now, e to the 0 is a 1. Cosine of 1 and sine of 1, they don't really get much better. In particular, I'm fairly certain that both of these are even transcendental numbers, so they're kind of worse than irrational. But you can take as an approximate value for them 0.543 and 0.8415, approximately. So, nevertheless, we have an approximation for e to the I, or we have this non-approximate value that still involves cosines and sines. Actually, before we do part C, we have to talk about the most beautiful equation. So we're going to do e to the pi I, so that's 0 plus pi I. And that's going to be with our formula, e to the real part, cosine of the imaginary part, plus I sine of the imaginary part. E to the 0 is 1. Cosine of pi is negative 1. Sine of pi is 0. So we get 1 times negative 1 or negative 1. And the far left side here is e to the pi I. This is one version of the most beautiful equation. Another version is obtained by adding 1 to both sides. And this is called the most beautiful equation. Well, you can check why, but it involves 5 of the most useful constants for some definition of the word useful. But nevertheless, you can't start talking about the complex exponential without saying what that is. All right, let's do a slightly more involved example. This is C. We're going to look at e to the 2 plus pi I. So we have e squared cosine pi plus I sine pi. That's the rule. Again, 0, negative 1, we get negative e squared. We'll see in a little bit that the complex exponential behaves nicely with respect to the usual exponential rules. So we could have done this differently. We could have written e to the 2 plus pi I as e squared times e to the pi I, and we just computed e to the pi I was negative 1. So we get the same answer using what we're used to with the exponential rules.